Have you ever noticed how when you hear a car coming towards you and it has a horn or a siren going, that the sound suddenly changes as soon as the car passes you? The pitch of that horn suddenly goes down once it passes you. Well, this is an example of the Doppler effect, in which the frequency that you observe depends on the relative motion between you, the observer, and the source of that sound. Now, it turns out that the Doppler effect is completely general for all types of waves, whether they're light waves or sound waves or other examples of waves. In this lesson, we're going to learn an equation that describes the Doppler effect for sound, but keep in mind that Doppler effect can occur for light too. The equation's a little different. But the Doppler effect for light is super useful, and it's used in astronomy and radar guns and all kinds of interesting applications. Now, I noticed something in our textbook, which is that the textbook spends like 4 sections or something on the Doppler effect for all these scenarios of one observer moving towards the source, observer moving away, just all this stuff. It's too much. There's only one equation you need to know, and it describes all possibilities of relative motion between source and observer. Here's the one equation. The frequency that the observer hears is the frequency that the source generates times the speed of sound plus the velocity of the observer divided by the speed of sound minus the velocity of the source. So let me just say once again what all these things mean. FO is the frequency that the observer hears. Fs is the frequency that the source generates. V is the speed of sound. VO is the velocity of the observer, and we need to keep the signs straight. So it's positive if the observer is moving toward the source. It's negative if it's moving away from the source. Likewise, Vs is the velocity of the sound source It's positive if the source is moving toward the observer. And negative if it's moving away from the observer. Now, if either the observer or the source is stationary, you just use 0 for their velocity. And now that takes all of those like 4 possibilities that the textbook spent so long worrying about into account. Let's do an example. Example 14.5. You have an ambulance that's traveling at 75 miles per hour. Oh great, you have to do unit conversion. And its sirens have a frequency of 400 hertz. A car is traveling 55 miles per hour in the opposite direction. So what frequency does the driver of the car hear when two vehicles are approaching each other and then when after they've passed each other? So first we'll need to convert these speeds to meters per second. Alternatively, you could express the speed of sound in miles per hour. As long as all of these speeds have the same units, it doesn't matter which units you use. So either we convert these two to meters per second, or we convert the speed of sound to miles per hour. But I'll just convert these to meters per second. So this one is 26.4, and that one is 33.5. Okay, so first scenario, the two vehicles are approaching one another. Like that. I guess if we're driving in the US, they would be approaching each other like this. Driving on the right side of the road. So when they're approaching, we say that Vs is positive and Vo is positive. They're both approaching each other, so both of these velocities are positive. So the frequency that the observer hears is the source frequency. The source frequency is what the siren would sound like if everything was stationary. So when everybody's stationary, that siren plays a 400 hertz tone. Now we use V, the speed of sound. And, I think there's one more fact in this problem. Yeah, one more thing to worry about. They told us the air temperature. It was 24 degrees C. So you need to use the speed of sound equation to find the speed of sound at 24 degrees C. I'll let you do that, and I'll just write down the answer. It was 345 meters per second, a little bit faster than room temperature, where it's 343. And now let's just get our signs correct. VO, we add it, it's positive, 26.4 meters per second. And on the bottom, we subtract VS, which is positive, .475 hertz. That's a significantly higher frequency than a siren has when it's stationary. So that will sound like a higher pitch. Now part B, these two vehicles have passed each other. Here's the observer. There's the source. By the way, the observer, if the observer saw an emergency vehicle with sirens, they probably should have pulled over and stopped. But that's not what happened in this problem. They kept driving. So they've passed each other. They're now moving away from one another, but we're assuming that the siren on this emergency vehicle, on this ambulance, is maybe generating spherical waves so they go out in all directions, even behind it. So now the observer hears 400 hertz, 345. Now we got to get the signs right. Now we add negative 33.5 meters per second. I'm dropping the units because they're all going to cancel anyway. And we have 345 minus negative 26.4. Okay, they're moving away from each other, so now we say that V, I should have written this earlier, Vs is negative 33.5 and VO is negative 26.4. So keep track of all those negative signs, and if you do, you'll get 339 hertz, which is a significantly lower frequency, a lower pitch. So the siren goes from sounding somewhat high pitched to somewhat low pitched as the observer passes by. That's it.